Okay, so in this lecture, we are gonna discuss the concept of what a cyclic subspace is. Okay, the concept of a cyclic subspace. Previously, we have discussed the concept of what a diagonalizable linear operator is, right? Now our goal is to typically study two other very important forms, I should say matrix forms of a linear operator, which are the rational canonical form, which are typically called the rational canonical form, and the Jordan canonical form. And the Jordan canonical form. Okay. So our goal is to now study these two important forms. And to have an efficient understanding of these forms, we need to start with the concept of cyclic subspace. Okay. Okay. So how does the concept of cyclic subspace typically comes into existence? Basically, if we have a finite dimensional vector space and we define a linear operator on it, then our goal is to attain the smallest T invariant subspace of V. Right? I'll ask the viewers to go and watch the videos in my playlist where I have discussed about what T invariant subspaces are and concepts related to that. You might also read it from somewhere else, but you should have already have the knowledge of what T invariant subspaces are and what annihilating polynomials are, minimal polynomials are, so on and so forth. Okay. So our goal is to typically form the smallest T invariant subspace of V. Okay. So let V be a finite dimensional vector space over a field F. Okay. This is given to us. We consider a linear operator on V. Okay. Now our goal is basically find the smallest T invariant subspace of V. Okay, T invariant subspace of V. Now, one obvious way to do is that take the intersection of all T invariant subspaces of V. Or we have something more. We need to find the smallest T invariant subspace of V which contains a certain element alpha. Okay, which contains alpha in V. And we choose an element alpha from V as well. Okay. Now, what is one obvious way to do this? One obvious way to do is to just take the intersection of all the T invariant subspaces containing alpha. Of all the T invariant subspaces containing alpha. Yeah. But that won't be a very fruitful procedure. The procedure we will be following to construct such a subspace will be something else. Okay. What we do is that we consider a subspace of alpha say V. Let W be a subspace of V. Okay. And alpha is in V. Alpha is in W. Now, if W is T invariant, that is, let W be T invariant. So, if W is T invariant, then what can we say? We can say that if alpha is in W, then T alpha is also in W. But that would imply that T squared alpha will also be in W. And we can keep on doing like this till we get that some T to the power R alpha is also in W, where R is some natural number. Okay. But that typically means that if I choose any polynomial from the underlying field, let G be a polynomial, let G be a polynomial, then if T alpha, T squared alpha, any T to the power R alpha are all in W, then we can obviously take the linear combination of them, which will eventually give us the form of a polynomial, right? Then GT of alpha is also an element of W, right? Is it clear? What we do is that we consider the set which contains all the vectors of this form, right? So consider the set of all vectors of the form GT of alpha, okay, where alpha is a certain vector in V, alpha is a certain vector in V, and G is a polynomial. So suppose if I consider V to be a vector space over the field F, then G is a polynomial from F over F. Okay. Is this a T invariant? Because what will be the image of any vector of this form under T? So you can just view it by just expanding the expression, right? Suppose GT of alpha has this form. Suppose this is summation I is equals to 0 to say k, say AI T to the power I alpha. That typically means that T of G alpha is T of GT of alpha is summation I is equals to 0 to k. AI's are typically constant, right? So they are not of so AI will simply come out of the under the image T, right? So it becomes T to the power I plus 1. But this polynomial is still inside the set, right? Because it is still a polynomial, right? It is still a polynomial. Is it clear? So therefore it's obviously a T invariant set. Okay. And by the way this is constructed, it's obvious that this set is the smallest T invariant subspace of V containing alpha, right? This set is the smallest T invariant subspace of V which contains alpha, right? So this set is typically what we call the cyclic subspace generated by the element alpha, okay, which is the topic of this lecture. So let me now come to the definition. So if alpha belongs to V, the T cyclic subspace generated by alpha is the subspace. So we typically denote this as Z alpha T, the subspace Z alpha T of all vectors of the form. So it's obviously of the form GT of alpha, where G is a polynomial. G is a polynomial and T is obviously a linear operator. T is a linear operator. Is it clear? One more definition comes straight away from this definition is that if the T cyclic subspace generated by alpha equals the whole vector space V, okay, then alpha is called the cyclic vector for T. It's called the cyclic vector for T. Okay, the term the why we have used the term cyclic will be clear in a few moments. So this is the basic thing. Let us study a few examples related to this. So example number 1. What happens if you consider the zero element? If you consider the zero element under any linear operator, we know that the image of the zero element under any linear operator is basically 0, right? So this is nothing but the zero subspace, right? Number two, um, this is a very you can think of this as a lemma, that the T cyclic subspace generated by alpha, so it is one dimensional if and only if alpha is an eigenvector of T in V. Okay. How do we prove this? How do we think of proving this? Just see what happens. See, if Z alpha T is one dimensional, then that means that the Z alpha T is a span of the vector alpha, because alpha must be inside Z alpha T at any cost. The way Z alpha T has been defined, right? So it's a span of alpha. So every element inside Z alpha T is some scalar multiple of alpha. Right? In particular, if I choose the polynomial, if I choose the identity polynomial from the underlying field, okay, every element in Z alpha T is of this form, right? GT of alpha. So if I choose the identity operator, suppose G of X is X, then what is GT of alpha? Then GT of alpha is T alpha, right? Then T alpha, by this definition, then T alpha must be some scalar multiple of alpha, right? And obviously we have discussed about the fact that what happens if alpha is 0. So in this case, obviously we can consider alpha to be non-zero, right? So the statement 2 is typically for alpha being non-zero. Just let me write it here. That is, alpha is non-zero, right? So if T alpha is equals to C alpha, where C is some scalar and alpha is non-zero, then that obviously means alpha is an eigenvector, right? What can we say about the converse? If alpha is an eigenvector, what will happen? So if alpha is an eigenvector, then obviously there will exists a scalar C, right? Such that T of alpha must be equals to C alpha, right? But if T of alpha is equals to C alpha, then what is T square of alpha? So T square of alpha is, or we had discussed a property, or I should say a statement about these eigenvectors, that if T of alpha is equals to C alpha, then if you choose any polynomial, then GT of alpha is typically GC of alpha, right? These sorts of statements we have covered in the eigenvalue, eigenvector part 1 or part 2, one of them I guess. But this is again a scalar quantity, right? Scalar quantity. Therefore, any polynomial you choose from Z alpha T, it's some scalar multiple of alpha. But in other words, that means that Z alpha T is the span of alpha, right? Span of. And alpha it's a single element, single non-zero element, so it's obviously linearly independent. We don't, so it's obviously a basis element, which implies that Z alpha T is one dimensional, right? Yeah, this was fairly easy. What happens if we choose the identity operator? Let's say, let me change the color of the page. One sec. Yeah, yeah. Let me change the color of the page. Correct. Okay. Yeah. Okay. So now we choose T to be the identity operator. What will happen then? Then it's obvious that if T is the identity operator, then what is GT of alpha? So GT of alpha will typically be a span of alpha, right? It will be a span of alpha, or I should say some linear combination of alpha will be a more precise statement. Some linear combination of alpha, right? So that typically means that Z alpha t is one dimensional if t is the identity operator. Clear? Now it's obvious from the definition of a cyclic vector is that, so if we choose t to be the identity operator, then what can we say about the condition if alpha is a cyclic vector? So if Z alpha t is one dimensional, then what can we conclude from here? That if alpha is a cyclic vector, then dimension of the vector space V, because if alpha is a cyclic vector, then Z alpha t is nothing but V. Then dimension of V must be equal to 1. And has an obvious converse, right? That if dimension of V is 1 and V, so it's obviously alpha obviously becomes a cyclic vector, right? Because if dimension of V is 1, then it's obviously some linear combination of alpha, which we can imply back to the fact of this, right? We can choose T to be the identity operator, relate these two things, and then we can say that V is exactly equal to Z alpha of T, and then alpha typically becomes a cyclic vector, right? Thus, we can say that alpha is a cyclic vector if and only if dimension of V is equal to 1 for the identity operator. For the identity operator. Clear? Let us understand one more example. Okay. So this example is quite related to the vector spaces which we have already used. We consider the two tuple field. Okay. We consider the two tuple field, which obviously consists of ordered pairs of elements such that each element A and B are from the field F. Okay. We consider the standard basis of F2. Let B be the standard basis of F2, that is B consists of the elements E1 and E2, where E1 is the vector 1 0, E2 is the vector 0 1. Okay. We choose an operator on F2. Let T be an operator on F2 such that the matrix of T with respect to this ordered basis is this matrix. It's 0 0 1 0. Clear? What can we say about the existence of an existence of a cyclic vector? Okay. So we choose the vector E1. Okay. What can we say about A E1? That is, so what is A E1? A E1 is typically the image of E1 under T, right? So what is A E1? So it's 0 0 1 0 times the vector 1 0, but it is typically coming out to be the vector 0 1, but that is equal to E2, right? And what can we say about A square E1? It's 0, right? It's 0, right? But then observe one thing from here, that we got T of E1 to be E1, sorry, T of E1 to be E2, and E1 is there on itself. Let me just rephrase this. Yeah. So we have E1 and we have the vector T of E1, right? Now, one more thing to consider about Z alpha T, by the way Z alpha T is constructed, isn't this the span of the vectors of the form T to the power K alpha such that K is greater than or equal to 0, right? So it's typically the span of the vectors alpha, T squared alpha, and so on, right? That's why the term cyclic has come. So it's sort of a cyclic set, you might say. It keeps on getting generated, the elements keeps on getting generated by implying T on the vector which we previously have. Clear? So if you relate this to this, then this is the span of this is exactly Z alpha t, right? But T of E1 is typically E2, so this is exactly equal to V, sorry, F2. Yeah, we had considered V to be F2, right? So what does this implies? This implies that E1 is a cyclic vector. Okay, cyclic vector for T. We cannot say anything about E2. We cannot say anything about E2. The reason is that what is A of E2? So it's 0, 0, 1, 0 times 0, 1, which comes out to be uh, the zero column matrix. So it's 0 times 0, 1. Right? So typically E2 comes out to be an eigenvector. Right? It comes out to be an eigenvector. Therefore, Z E2T is a one-dimensional space generated by E2. This we have also studied that, right? That if E2 is if alpha is an eigenvector of the operator T, then Z alpha T is a one-dimensional space, right? But it needs to be two-dimensional for it to be a cyclic vector, because the vector space which we are working with is a two-dimensional vector space, right? Okay, so let this lecture be up till this much. In the next lecture, we will be discussing certain properties and theorems related to cyclic subspaces. We will introduce a very important concept, that is concept of a T annihilator of a vector alpha. Previously, we had discussed, what annihilators of operators are. Right? Here we will discuss annihilators of a certain vector. And using this concept, we will come up with a very important form of a matrix, which is called a companion matrix. And it has very beautiful consequences. So meet you guys in the next lecture.